Hello everyone, friends. I'm back with the second lesson in our Tekla training video series. I'm Ali Olgun. As you recall, in our first lesson, we focused on the program's basic working logic. We discussed the basic working logic of the design screen. You know this area, we call it the design screen. We talked about the screen where assembly and manufacturing drawings are arranged, the section under drawings and reports, after our model and design are complete. We discussed the output section, the drawing list, and then the manufacturing phase, which, as you know, involves adjustments to manufacturing drawings under the drawing list, and general assembly drawings, including part cuts, assembly, and general assembly drawings. Here, cut, join, and fix in place were the three stages. After this brief recap, today I'm talking about the topic of our second lesson. Friends, we'll discuss basic modeling concepts. These two videos are crucial. Friends, we'll cover the program's logic and modeling, basic modeling concepts. These two videos are vital because our upcoming videos will focus on application and starting a new model in Tekla. But these two videos are truly essential. If we grasp these two foundations correctly, understanding the program's basic logic, modeling, and core concepts, we'll progress much more smoothly. You won't be left wondering how we got here. There won't be any confusion about our progress. In basic modeling concepts, the first step is data collection. Friends, what's this data? It's the steel structure or 3D form we're asked to design. Before we even open Tekla, we need to do some prep work. We must gather data, width, length, height, and so on. You're familiar with the X, Y, Z coordinate system, right? It's there in Tekla's design screen. In the bottom right corner of the Tekla design screen, there's an X, Y, Z coordinate system. This is our reference point. We're positioned like this. X is the horizontal plane, Y is the vertical plane, and Z is the depth. This defines our space. Before we input data here, we need to consider our position in this X, Y, Z system. We must collect this data relative to the 0 point, regardless of the project we're working on. For every project, we need to do preliminary work and keep it documented for constant reference. We must accurately determine the X, Y, Z coordinates. This is crucial for our work. What are X, Y, Z coordinates? Let's say we're dealing with a porch system as an example. It doesn't come to us in 3D. We receive it as a 2D plane. We need to note these down. Let's look at the accessor system where we'll place the columns. And Z. It is the system that describes the plane to us, friends. I will talk about this accessor in detail during the modeling phase. Now I will briefly talk about it. When we double click on this accessor, you see the data here in the AK system. Friends, E data in the X, Y, Z plane. These are the 8 that I just mentioned in the X plane. Look, I said 8x 6,250 by 8 a.m. It was 6,250 apart. So that's 1, 1, 2, 3, 4, 5, 6, 7, 8, then 2x 5,550. We left a space and said 2x 5,550. This means that the spacing of the two axles at the end is 10,000 in the Y plane and 110. We divided it into 100 between A and B here. As you can see, 19,000 is B. The distance between C and C is 19 meters. So we are working here in millimeters. Friends, we are working in millimeters. We need to enter the Z plane. We start from 0. For example, it went as 500, 1,000, 9,000, 300, 1050, 11.800. Judging by the appearance of one of his accents, this is also the following, guys. 0 plus 050 is what you see here. We write it as a meter at the bottom. It is not very important. I will talk about them later. This is what we call data. We accurately note the X, Y, Z coordinates and input them here. I'll discuss data entry in our upcoming videos. Since I'm covering basic modeling concepts now, let's briefly touch on this to give you a general idea for future reference. Now the next stage is the fast concept, which is part of the design phase. The concept of phase is crucial. What is a phase, folks? Let me give an example. AutoCAD users surely know about layers. You create columns on one layer, beams on another, axes on a different one, and even dimensioning on its own layer. This makes filtering easier and helps you find objects more quickly later on. You can open, filter, delete, and modify. This concept, similar to Tekla X style, offers great convenience. The fast concept is like AutoCAD's layers. So what is a fast? When we open our main program and start modeling under Tools Phase Manager, you'll see created phases. These you can customize as you prefer. I've created phases to simplify my work, including new basic steel columns and beams. The aim is to prevent conflicts and easily find what we need later. Now, if I click on the steel column phase once and select Object Bay, it highlights all steel columns at once. Did you see how it marks phase 3? It's the steel input phase. Look, friends, when I select Object by Phase, it doesn't show the steel input. But watch this. If we mark the steel scissors, it instantly reveals all of them. So, what's the lesson? Before we start modeling, we need to set up our phases and design through them. Got it? We've started modeling but haven't added columns yet. What's next? Let's go to Tools Phase Manager and click Add. We're creating a new phase here. I'm explaining quickly now since we haven't started the application yet. I'll detail everything step by step later. When we click Add, we create a new phase. You can create as many phases as you need initially for columns, sheets, and diagonals. This will make your work easier. For example, you can use phases to filter object groups. I can select just phase 3 to be visible, show only columns, or display everything except columns. He hid some columns and showed others. As you can see, friends, phasing is a concept that makes our job incredibly easy. After discussing phasing, I'll give you some info on part and assembly naming and note-taking. Now, friends, in our program, part and assembly names are very important. Why are they important? Our goal isn't just to finish the design here, but to ensure that When placing an element, we need to consider the following stages. How do I prepare the manufacturing drawings? How will the steel workshop read and cut this part? How will the welder assemble the cut pieces? Can these assembled parts be shipped to the construction site? If you make a piece longer than 2 meters, there are no profiles longer than 12 meters. The site can't find this, and you must keep this in mind. You have to think about multiple things simultaneously for each element. First, how will I prepare the drawings? How will the workshop cut this? How will the welder assemble it? And how will it be transported to the site? How will the assembly technicians at the construction site join these incoming parts? If you can logically answer all questions, place that element there and finish the design. Otherwise, rushing without thinking everything through means you'll have to fix it later, wasting your efforts. Now, why are part and assembly names so important? They're crucial for finding parts and for workshop cutting processes. Each part has two names, a part name and an assembly name. Remember the part and assembly concepts from our first lesson? That's where this comes from. They're separate parts with distinct names, like this block. It's an assembly. This block has its own name and might consist of 10 separate parts. It depends on how you create the assembly. Let's look at a column. Double-clicking it shows what data it needs, the part name and the assembly name. It's asking for two names. The brand wants a name. Top is brand, bottom is name. Asks what name to use, profile cross-section, and material quality. Color is here, friends. We'll cover these in detail from Lesson 3 when we start application drawings. Now, PC is the part name. Note these down for which column. I named it. What name for the casing, crossmember, and cleats? Make a chart. Part names, assembly names, layer names. Write down what you named each and its phase. I'll show an example. This way, you won't forget and can directly in your notebook, you'll find the part name PC. I put P in front to indicate it's a part. When you see P, it means it's a part. In assembly, I use B to show it's a combined element. The C next to P comes from column in English, meaning it's a column part. It indicates that it's part of the column. You see the C next to the joint in both cases, meaning it's a column joint element. Let's look at the cross-section, friends. The P and B at the start always mean part. R means it's a cross-section. I code it this way, but you can use different coding. Try not to change the initial P and B much. Why do we label them like this, friends? To find and describe what we're looking for. For scissors, part means scissor parts. Joint means scissor joint elements. Now our design is done. How will we find what we need? Let's say we're getting part cuts. Look, friends, if I roughly select these and have them cut into parts. Yes, guys. Now I mentioned part and assembly names. Let me show you an example. Look, when I tell the program to show only the names of single parts, you see it does. Remember I mentioned columns earlier? Well, here the PC makes our job much easier. The C's, I understand, are all column-related parts. If I wanted to edit PCs, or if I had given them all one name, say P for Paris, I wouldn't know which part belonged to what, column, beam, or truss. But by adding another letter next to P, like C, I know all these are column parts. If there's an M, I know they're truss parts. For example, if I open PM1, you can see it's a plate. Or looking at assemblies, you see the same logic. Notice all these P's at the start. Each indicates it's a part. When I look at the assembly, I see B at the start of each item. These B's represent assemblies. If there's a U next to B, I know it's for overhangs. For example, BU indicates a bottom overhang assembly. G stands for tension rod, and R next to B means it's for diagonal crosses. You'll see how helpful this is in our detailed lessons. This system prevents confusion and helps manage the numerous parts and assemblies in even a simple porch project. Without it, you'd easily get lost in the hundreds of components. If you don't take notes and can't track which part goes where or belongs to which element, you'll struggle to answer questions or find things when asked. Making revisions will be a nightmare. So, friends, use separate part and assembly numbers for columns, beams, and tension rods. We need to properly assign part and assembly numbers to all elements separately and note them down correctly. What did I tell you about note-taking? It's our final topic. Create a ruler or list for yourself in a blank notebook. This will be your design notebook. Write place of use here, friends. I'll share a photo of my own note-taking system. Divide it into sections: place of use, part name, assembly name, layer, and phase. In place of use, write where it's used, column or beam. Next to part name, write PC for column, BC for beam. In assembly, BC means connection. In layer, write column or beam in English. In phase, note which phase it belongs to. For example, steel columns are in phase 3. By writing this down, you won't need to keep checking here. You can refer to your notebook to see which phase it belongs to. Our second lesson is on basic modeling concepts, folks. That's all. See you in our next lesson. Goodbye.